Hello, this will be the first video in a series of videos where we're going to introduce concepts associated with linear programming. And so in this video, we're just going to work on going from a problem statement, which is what you're seeing before you, and eventually end with a mathematical model, which is a description or a representation of the problem at hand. And then in follow-on videos, I will create that will actually show how to take that mathematical model and run it through a solver, whether it be in Microsoft Excel or a graphical method or using Pyomo plus GLPK, and actually solve the model and interpret the results. Also, just so you know, the GitHub page that we're looking at for the problem statement will be linked in the description of this video on YouTube as well. So with that being said, let's go ahead and hop right in. So the problem that we're going to look at is a kind of classic product mix problem. And so product mix problems are basically the idea that you have multiple products that you're trying to manufacture, and you're trying to figure out what combination of these products will yield the maximum profit in this case. And so here we're going to have a fairly simple model where we're going to be working at this Easy Riders company, and they just have two products. They've got kind of a budget line product that we call the Economy Rider that sells for 99 cents, and then we have a more premium pencil that is the Deluxe Rider that sells for $1.75. And the ultimate goal here is going to be to maximize the total profit that is generated through this production run. So we know the sell prices of each product, but we also have to keep in consideration the labor and material constraints that we need to acknowledge. And so first we've got labor constraints here. So the production of these pencils happens within 4 different departments. You can see the pre-processing, the curing, the shaping, and the assembly. And each one of those departments has a set number of labor hours that will be its capacity, which is on the far right-hand side here. Now, when we go to make a single instance of either the Economy Rider or the Deluxe Rider, we'll consume some of that labor. And so notice these two columns are in seconds. So for the Economy Rider, it spends 2 seconds in pre-processing, 3.5 seconds in curing, 1.25 seconds in shaping, and 8 seconds in assembly. Similarly for the Deluxe Rider there. So as you can see, we can't just make an infinite number of these pencils, right? We would be at some point bound by the amount of labor that we have in an individual department there. And so this information we'll be using to create our model. And also we need to recognize there is a cost for this labor, and that's right here. You can see it, 65 cents per minute will be the shop labor rate there. Because obviously, when we talk about maximizing the profit, we have to realize we're going to have a source of revenue by selling these at these two prices, but then we're going to have labor cost associated with this 65 cents per minute, and we're also going to have material costs. And so that's what we're coming to down here. So this first table here illustrates a bill of material for the Economy Rider and the Deluxe Rider products. You can see the bill of material comes up with these cedar blanks, which are basically sections of wood that they cut up into individual pencils. Notice every one of these blanks, it makes up 10 pencils. That's why the unit amount of the cedar blank for each one of these is 0.1 or 1/10 of the entire cedar blank. Then we've got glue that'll hold the lead into the cedar blanks. Then we've got different types of finishes depending on whether it's an Economy Rider or a Deluxe Rider. The ferrule is just kind of that metal piece that's going to hold the eraser, and then we've also got this grip kind of accessory that goes on to the Deluxe Rider only. So now that we know what every one of these products is made of, we also need to look at the overall inventory we have of each of these components, and that's this second table. So for instance, for the cedar blanks, we have 15,000 instances of the cedar blanks, and each instance costs 15 cents. We're also going to have to be careful with units a little bit here, because notice for the glue, the unit of measure down here is in pounds, so we have 1,250 pounds, but the bill of material shows that value in ounces there, just because it's more convenient to me as I look at the bill of material. And this cost here is per pound, since it's in with the unit of measure, so it's 75 cents per pound of glue. All things that we'll be using to look and account for the material cost when we go to build what would be the objective function here in a moment. And finally, the business considerations. One of the things we need to think about in this problem is the idea that we have a large demand on our factory in such a way that we don't have to worry about making too many products such that we have excess, right? We've saturated the market already, and we're now having to store finished products in some sort of inventory location. That's not going to be the case. We're going to assume that every product that we make can be sold. All right, so that is a very quick rundown of our problem statement. And so the idea is now to take this problem statement, the goal being to maximize profit, and turn this into a mathematical model, specifically a linear programming model. And so to do that, we'll be working over here, and I will just be jotting a few notes and building our model as we go. So what's common to these linear programming problems is the idea that we have to define what are called decision variables. And so decision variables represent the things that I, as the analyst, or I as kind of the production planner in this instance, have the ability to control. And so if I look back over here, and as I've described the problem, one thing that I can control is the amount of each product that I produce. As far as, hey, I'm creating a production plan for the factory, and I need to tell the factory to make X number of economy riders and Y number of deluxe riders there. And then they, of course, go and run those production runs. So our decision variables here, the things that we can control, are going to be the quantities of each product to produce. So we'll write that as I'll say X sub E, which is an element of the reals, be a quantity of economy pencils. This will be to produce. And then X sub D, which is also an element of the reals, be a quantity of the deluxe pencils. To produce. Okay, so a few things that I've done here is I've described the two decision variables. I call it X sub B and X sub D. They're elements of the real. That's what this statement is. This right here is the symbol to represent an element of, and this scripted R here is a notation for the real number system. So essentially we are saying, hey, I'm going to be manipulating two continuously real numbers, and that'll be the knobs, if you will, are the things that our solver is going to be able to manipulate. And you might be thinking to yourself, hang on, Brock, that's all good and all, but does that fit our problem exactly? What I mean by that is you might be saying, well, if I'm going to make pencils, does it really make sense to make a fractional pencil? In this case, these are real numbers, so I could end up with saying things like, well, make 1,252.345, and that 0.345 is a fractional bit of a pencil. And you would be correct. Okay, that doesn't fit our model exactly, but this is going to be a simplification that we're going to run for this kind of introductory video. Also, I could argue that in this specific problem, we are going to probably be making lots of these things, several hundreds, a few thousands maybe, of these pencils, and each one of these pencils, I'm betting, is going to have a fairly small unit profit contribution. So those two things in combination basically allow me to say things like, well, yeah, you're correct that I really need these to be integers, but if I run them as real numbers, then I could come up with a solution that is optimal for the real numbers, and then I could apply a mathematical floor function, or basically rounding down to the nearest integer. At that point, I am not necessarily guaranteed that I'm going to have an optimal solution, but I am going to have a very, very, very good solution there. And so it may be okay if I go with the simpler model and then be able to come up with a very near to optimal solution, as opposed to introducing what is going to be the more complex methods associated with imposing integer requirements on these variables and coming up with the optimal solution there. And so that's my argument for allowing these to be real numbers at this point. I'll make future videos where we talk through the consequences and what happens when we say things like, well, let's make sure that these are integers. But for today, let's just let them go as reals. Okay, with that being said, I've now defined my decision variables. The decision variables are going to be the quantity of each of these types of pencils to produce. The next thing that we go to when we talk about these linear programming problems is they all have what would be an objective function. So let's work on that next. So we are going to work on an objective function. And the objective function is basically the goal which we are seeking. And so for our problem, we are seeking the maximization of profit. And that's a fairly common thing. We'd maximize profit, maximize revenue, something along those lines. But we could also minimize something as well, right? We might try to minimize a cost, for instance, as well. But in this case, we said we're maximizing profit. And so we need to think about first, well, what is profit? Well, that's going to be the revenue we create from selling the products minus, we're going to have some labor cost in here, and then minus also the material cost. So what we need to do is develop a mathematical expression that describes the profit, and here's the kind of pieces of that mathematical expression, and they are also going to have to use these decision variables, which hopefully makes sense given the context of the problem. So let's start with probably the easiest one on the far left here is revenue. So revenue here is equal to something. Well, if I look back at my problem statement, I have the unit selling price for the economy writer and the unit selling price for the deluxe writer. So if I say, hey, I'm going to sell XE number of economy writers, the total revenue generated for that would be 0.99 XE. And then the same thing for the deluxe writers, it would be 1.75 X sub D. And so we want to sum that for the total revenue generated. So writing that out, it'd be 0.99 X sub B plus 1.75 X sub D. And this would be our equation to describe the amount of revenue that we're going to generate by producing XE, quantity of economy pencils, and XD, quantity of deluxe pencils. Fairly straightforward at this point. So now let's look into our labor cost. So the labor cost, we have a little bit of a problem here, just because I've introduced 3 different types of time units for this description in the problem statement. I've got a labor rate, which is $0.65 or 65 cents per minute. I've got a capacity in hours, and I've got these individual time consumptions or burdens, if you will, in seconds there. So we're kind of all over the place. And what we need to be able to do is move those all into a single unit of time for the sake of the model. And really, me as the person modeling the problem would have my pick as far as I could do it in seconds, I could do it in minutes, I could do it in hours. It's really up to you. In this case, I'm going to roll everything up to the biggest unit, and I'll do everything in hours. So the first thing I'm going to do is convert that $65 per minute and do some dollars per hour for the labor rate. So let's do that right here. The labor rate, we are given it as 65 cents per minute. And I want to convert that to something per hour. So set up this little unit conversion here, and I need to multiply it by 60. And just FYI, I'm going to be using a Jupyter Notebook for these type of simple calculations as we go through this process. And it looks like that is $39 per hour. So that is equivalent to saying it costs $39 per hour for the shop labor rate. Alright, so looking good. So now that I've got the shop labor rate converted to dollars per hour, now I need to come up with a relationship that describes the total labor cost when I make XE and XD number of products. So one thing I can think about here is I could first look at how much labor in terms of time is consumed, and then I could obviously take that value and multiply by my labor rate to convert that to dollars. So let's work through that. And so one thing I can look at is right here. If I just look at the economy riders, I can look at this single column that I have in my table, and one economy rider will take 2 seconds in pre-processing, 3.5 seconds in curing, 1.25 seconds in shaping, and 8 seconds in assembly. So if I sum all that up, that would be the amount of labor time that is consumed by one economy rider. And then similarly for the deluxe rider. So we could start with doing that. So I'll say the labor cost is equal to, we'll do some work here, 2 and 3.5, 1.25 and 8, that's an X sub E, 2 and 3.5, 8.75 and 10, that's X sub D. So leaving it just the way I have now, this would be the amount of labor time in seconds for the production run, right? If I make XE and XD number of products, this is all in seconds at this point. So one thing that I want to do is convert it from seconds to hours. So I could multiply it by 1 over 3600, where this is essentially seconds and this is hours here. And remember that this whole thing here, maybe I'll make a note, something like this. This is all with a unit of seconds. So you can see I'll end up with a certain amount of hours there. And then I need to multiply it by my shop labor rate as well, right? That would get me to the amount of labor cost in dollars. Clean that up. So multiplying by $39 per hour, that would cross off, this crossed off with that seconds essentially, and I end up with a labor cost in seconds. I'll slide that up. Alright, so it's a little bit of a longer expression here, but just still an arithmetic or algebraic expression that we're working with. And if you look at this for a little bit, you'll notice that we can simplify it, and it's going to end up being some constant times x sub e plus some constant times x sub d. So let's work on calculating what those two constants are. And so to do that, I'm going to hop back into my Jupyter notebook here. I'll just write it into a variable that says unit labor econ. This will be the coefficient for us. And so it's 2 plus 3.5 plus 1.25 plus 8 times 39 divided by 3600. And we'll just print out what that value is. And so I'm ended up with 0.1598 for my coefficient that'll be in front of x sub b. And so we'll do a similar thing for the deluxe pencils. And 0.2627. All right, so that's looking good at this point. So 0.1598. So I can say this is approximately 0.1598 x sub e plus 0.2627 x sub d there. And so now I've got a description of the labor cost when I make a certain number of economy pencils and a certain number of deluxe pencils. So things are shaping up quite well. So I look back up here, the only thing I have left to consider is the material cost, and then I'll be able to come up with our profit description. So now let's make a little spot to work on material cost. Alright, so the materials, we'll need to know information about the bill of material as well as our inventory table down here as well. And so we can kind of follow a similar line of thought to what we just did for the labor, and we could look at every one of these components and calculate the cost that would be generated by using that component when we run our production run. And so in this case, for instance, if we made a certain number of economy and deluxe writers, it'd be the sum of those times 0.1. That would be the amount of cedar blanks that we use. And then we'd be multiplying that by 15 cents in order to come up with the cost associated with the cedar blanks. We'll also have to be careful once we get to some of the other ones that are described in terms of weights. In this case, glue would be our first one. Notice in the bill of material again, it's in ounces, and in the inventory table down here, it's in pounds. So we'll need to pick a consistent unit here. Let's roll it up again to the bigger unit and use everything in pounds here. So I'll need to make sure I divide this 1.5 by 16 to go from ounces to pounds when I go to here. And so I think what we can do, it'll be a rather long equation, but there will be a component for each one of the raw materials here. And then we'll write it all out as a material cost, and then we'll start grouping like terms similar to what we just did for the labor cost. So hopefully that gives us a little bit of a plan, and it'll become more clear as we start writing this expression out. So the material cost. Start with the cedar blanks. So the cedar blank, the quantity consumed, depending on which product I'm making, is a constant, 0.1. It doesn't vary at all. So I can write that as, if I make X sub E and X sub D, that would be the total amount of pencils that I produce. I can multiply that by 0.1. That tells me how many cedar blanks that I have. And then the cost per cedar blank is 0.15. And just to keep track here, these are the cedar blanks. And then we're going to have a similar expression as we go through all the other components. The glue, we've got 1.5 on each of the products. So we can write again X sub E plus X sub D times 1.5. Now remember, we're trying to get it to pounds, so we're going to divide by 16 there. And the cost is 75 cents. That is the glue. Alright, so next, moving on from the glue, we get to the basic lead. And this is the first time we have one that's only used in one product and not the other, right? The basic lead is only used in the economy writer, so we won't see any action here with the deluxe writer, or X sub D. So we'd have, the amount I would have here is X sub E times 3 over 16. And the cost of the basic lead is 45 cents. And then we'll go ahead and do the other one as well. If I'm looking at the smooth lead, it's 3.5 and only used for the deluxe. That is a 6. And the smooth lead costs 64 cents. Alright, this is the basic and the smooth lead. Writing this in blue just to mainly keep track myself where I'm at. Alright, basic lead, smooth lead, now we're on to the finishes. We've got matte paint and the wood stain, so the matte paint's only used in the economy. And it has a 57-cent unit price. And then the wood stain is only used in the deluxe. And it's 89 cents. And then we're down to the ferrule, the eraser, and the grip. And so the ferrule and the eraser, just one each on the component. So I'm going to scoot down here. This will be the ferrule, that's 10 cents. Then we've got the eraser, which is a nickel, or 5 cents. And then the grip finally, and the grip's only used in the deluxe, so it'll be XOB D times 13. There's one grip. $0.13, yes. And just go back and finish keeping track. Ferrule, eraser, and grip. Okay. So obviously a fairly lengthy written equation here, but I think we have covered all of our bases. And so this long description starting here and going all the way across and down the right hand side a little bit is describing the material cost. And again, it looks a little bit complicated, but you can kind of look at it and say, hey, this is just a bunch of algebraic terms, and really we can collect like terms here and get this something that looks very similar to this right here, where we've got a coefficient times x of e and a coefficient times x sub d there. So I will just write that right here, that this is going to be approximately some value. And so let's move this up to the top. And again, I'll go over to the keyboard and with my Jupyter notebook here, perform some computations. So this is going to be my material cost. Let's call it unit material econ. And so I'm looking at where all the x sub e terms will be at. So looking at the Cedar blanks, I'll have 0.15 times 0.1 plus 1.5 over 16 times 0.75. Now I'm on to the basic lead. 3/16 times 0.45. The smooth lead I get to skip because it only has the deluxe. Then I'm to the matte paint. Wood stain I get to skip. The ferrule 0.1. The eraser 0.05. And nothing for the grip there. And I end up with the material cost for every single economy pencil is right about 42 cents or so. And now we'll do the same thing for the deluxe pencil. So it starts off the same, 0.1 times 0.15 coming from the cedar blanks. The glue will be the same as well. Now we skip the basic lead and this time use the smooth lead. Smooth lead is 64 cents. There we go. Matte paint I don't have anything, but the wood stain I do use. And then the ferrule, the eraser, and this time I have a grip in here as well. And I end up with 0.64, so roughly 64 cents there. Alright, so collecting right terms, we come up with some coefficients that are close enough for what we're doing today. So in this case, we'll call it 0.41, I'll say 94 x sub b. And 0.6444 x sub d. Alright, so kind of recapping, we started our objective function here. We said it is revenue minus labor cost minus material cost. Right here is our relationship for revenue. And then here's the labor cost, and then here is the material cost there. So now we can finally write profit as a function of our two decision variables. Very good. So I'll come down here and say, hey, I'm actually going to write profit now. And I'll write it out like this. I think it was 99 cents was the sell price for the economy pencil. The labor cost was 0.1598. And then the material cost is 0.4194. It's all times x sub b. And then for our deluxe, I believe that was selling for $1.75. Labor cost is $26.27 after the decimal place. And then the material cost is 0.6444 x sub d. And again, I can reduce this down to a sum of a coefficient times x sub b and a coefficient times x sub d. So I'll call this unit profit econ is equal to 99 minus the variable for the economy labor cost minus the variable for the economy material cost. You get roughly 41 cents. And then similarly for the deluxe. and get about 84 cents there. So 0.41, shorten it to 2 decimal places at this point, 0.41 x sub e, whoops, plus 0.84 x sub d. Alright, so all of this work here really is again going to describing the objective function where we're trying to maximize profit, and we'll say maximize this algebraic expression right here because this is our description of how profit is going to increase as we make more of the economy pencils or more of the deluxe pencils there. Alright, so now we need to move on to actually writing the bulk of our linear program. And before I do that, I'm going to increase the size of this just a little bit. Give me 1 second. Alright, that'll do for now. Forgot to anchor it, but it's fine. Alright, so let's clean that up. And let's say this will be our LP model down here. Alright, so our linear programming model, what we're building up for here, is we need to write a model that describes first the objective function. Well, we're trying to maximize profit, we said. So that will be to maximize the profit, but I don't want to write profit here. I want to write this expression up here. So we'll say maximize 0.41 x sub e plus 0.84 x sub d. And then we'll say subject to, and we will list all of our constraints here. And so our constraints are going to be associated with both labor as well as material. So let's start with the labor constraints first, and maybe we'll make that in a different color here. Let's make our labor constraints red. So we have to make sure we don't violate any of these capacities. And so we've got these in hours, so we'll keep these in hours as well. So one thing we could say is, well, for the amount of economy writer pencils I make and the amount of deluxe writer pencils I make, I need to make sure that I don't exceed 12 hours. So to write that as a constraint, we could say something like, well, I'm just going to take 2 times x sub e plus 2 times x sub d. This would be the amount of time that we consume in the pre-processing department. This is the time in seconds, so we'd say, okay, that's 1 over 3600 to get us to hours, and we'd say that must be less than or equal to the 12 hours I have here. And this would be a description of the constraint that makes sure that we don't violate the pre-processing department's capacity. And we would do the same thing now for the 3 other ones. So we'd have 3.5 and 3.5 for curing. That was 8.25. The shaping is 1.25 and 8.75. and we'll have 13 hours. And notice here, what I'm doing is on the left-hand side, I'm generating an expression for how many labor hours I'm consuming during my production run, and I'm saying that's got to be less than or equal to my capacity on the right-hand side. This is 8 and 10. With a capacity of 18 hours. Okay. Well, maybe we'll just make some notes over here. This is associated with pre-processing. This was associated with the curing department. The shaping department and assembly. Okay, so this is the start of our mathematical model, and now we have a series of constraints that ensure that our optimal solution will not violate the capacity inside of each department. So that's great, except for that's really only one half of it, right? We also have the material side of things as well. And so we'll need to work on that bit. Add some more space down here. And so let's do that in a different color. Let's make this like a light gray here. So for that, we need to come back here and make sure we don't violate these inventory levels here. And so we'll have to be careful again because of units when we get to the weights in our ounces and pounds, but the other ones will be fairly straightforward. So let's go with cedar blanks first. I'm going to have 0.1 times x sub e plus 0.1 times x sub d. That's the total number of cedar blanks that I consume, and that's got to be less than or equal to 15,000. So let's just write that out. It's got to be less than or equal to the number of cedar blanks, 15,000. Now our glue, each of them use 1.5 ounces. A little ahead of myself there. Now that is the amount of ounces of glue that I would have to consume. So I'll divide that by 16 to convert from ounces to pounds. And make sure that I do not exceed my allowable inventory of glue here. And then we would do this for each of the other components. So I'll quickly go through that. It'd be 3/16 times x sub e here. This is for the basic lead, which is 950 pounds. The smooth lead here is 3.5 over 16 to get us to pounds, and we're only in the deluxe writers here. $17.50. Now we're at the matte paint, only used in the economy. $840. Wood stain 2.5 or 16, only used on the deluxe. £1,100. And then we've got the ferrules and the erasers and the grips. So the ferrules are we used one each, 10,000. The erasers are also used, one each. 32,000. Then we've got the grip, which is only used on the Deluxe Rider. There's 20,000 in inventory. All right, so I won't go through the time to annotate each one of these, but basically we walked through that table, and every one of these inequalities is going to ensure that we do not consume more than the allowable inventory of any given raw material. And so our model is almost complete, and the only thing that we need to do at this point is make sure we state that the x sub b and x sub d cannot be less than 0, right? Way up at the top of this, we said that they are real numbers. Well, real numbers obviously go on each side of the 0, and so we want to make sure that our solver knows that x sub e and x sub d must be greater than or equal to 0. Okay. It's been a little bit of a lengthy video, but hopefully you made it all the way through. And what you're seeing on the screen should be a representation of the linear programming model for this product mix example. Notice we are maximizing some mathematical expression which describes the net profit contribution that's going to be generated for this production run. And then we are saying it is subject to a series of constraints. The red constraints here all are indications that the labor in each department is not going to be exceeded. And then in gray down here, all except for the bottom one here, are indications that we are not going to exceed the allowable inventory for any given component that is used. And so what would be the next steps would be to take this, implement it in some sort of solver, whether you're doing it in Excel or in Python or in some other package, or you could possibly solve this by hand, and you would then arrive at optimal solutions for x sub b and x sub d. And one of the beautiful things about linear programming is that you don't just iteratively try every single possible combination of x sub b and x sub d, but there is a more elegant and a more efficient way to solve for the optimal solution, and that is the magic, if you will, of linear programming. So hopefully this all helps you to understand where we're going from a problem statement to a mathematical model, and then stay tuned and look out for future videos where we'll be looking at how to solve this model.